Hi, and welcome to this module where I'll be introducing you to various machine learning tasks. Right. So we already saw in the previous module that machine learning is essentially improving the performance of an artificial agent with experience. Right. So today we are going to look at first supervised learning, where the experience we're going to call the experience as training data here. So in this case, I'm showing you data points that is distributed in a 2D plane. So it could be, let's say, age and income that describe customers that come to a particular store, right? So in the case of supervised learning, this training data is going to carry labels, right? So it could be that whether the customer is going to buy a computer or not going to buy a computer. So the customers marked in green are going to buy a computer, and the customers marked in red are not going to buy a computer. So this is the kind of experience that's going to come to you. And in the case of classification task, which is this, so we're going to call it label training data, right, where the labels are drawn from a small discrete set. In this case, it's just yes or no. Right. So what is your goal here? So your goal in this problem is to figure out how are the yeses and nos distributed in this two-dimensional plane. Okay. So the simplest model for this is going to be to draw a straight line, right? So what does this straight line mean here? So it's essentially saying that people who have an income below a certain level are not going to buy the computer. People who have income above a certain level are going to buy the computer. Right. So if you think about it, we really gotten it more or less correct. There are a few points like that and that which are incorrectly classified, and here is another one who is actually going to buy a computer, but your classifier is going to say he's not going to buy a computer because it's on the wrong side of the line, right? So you can do better, right? So that's a slightly better classifier. So the two the red points that we had incorrectly classified previously, that one and that one, are now correctly classified, but we still are making a few errors. So what has happened from the previous classifier to this one is that we have made it slightly more complex. So if you think about it, the previous classifier was essentially saying x equal to some constant, right? So it is just saying income is equal to some number. If it's less than that, it's essentially no. If it's greater than that, it is yes. So now what has happened is we have added a slope to the line, right? It's no longer just based on the income, but the age also has to play a role here. So there are more parameters, right, that are needed for describing this classifier. Right? Earlier we just needed to have one parameter. Now we need at least two parameters to describe this classifier. So now can we do better? Obviously, right? So we can do better. We can draw a parabola like this, right? So in this case, you need more parameters, right? So you have ax squared plus bx. So you are now going to get additional parameters that you need to describe this classifier. So are we doing good here, or can we do better? It looks like we could do better because we still have an error, right? But it starts looking a little weird, right? So we are essentially now this is going to require a lot of parameters to describe what this classifier does. That little wiggle there that goes out and gets that additional red that you missed, right? And so now it becomes increasingly complicated. So what really was happening is probably that data point is a noisy point. It could be noisy due to a variety of factors. It could be that a person came to the shop to buy a computer, but for some reason he received a call and then had to leave immediately without buying one, or maybe the data has been erroneously recorded. The person actually bought a computer, but it has not been recorded. So there are several situations by which such noise could enter into the system, right? And we have to be very careful that we do not end up modeling such noise in the data, which will lead us to make really wrong predictions, okay, in the future data. So probably the best solution to this problem is this parabolic curve, because it gives us a good balance between the complexity of the classifier versus the accuracy that you have on the training data. So remember that. So this is all evaluated on the training data, and what you really are looking for is how well is this classifier going to work on the test data, on the deployment, right? So I'm going to train this classifier, and then I'm going to use this to predict whether the new customers who come to my store are going to buy a computer or not, right? So when I'm actually operating it with this new data, I want this classifier to do well, and therefore overfitting the classifier to the training data might be a bad idea, right? So one thing that you should remember here, right, is that my goal is not just to do well on the training data, right? If I'm only interested in doing well on the training data, right, what is the best way to do it? Yes, I just have to remember all the data points that was given to me, right? So I can never make a mistake ever again, right? I can be perfectly accurate in making predictions on my training data. But what I am interested in is to be able to perform well on data that I have not seen before, and therefore I need to be able to generalize to unseen data. And the only way I can generalize to unseen data is by making assumptions about the model. I have to make some kind of assumptions about what kind of lines, in this case, right? What kind of lines should be separating the buyers from the non-buyers, right? So whenever I have this kind of a need to generalize, it translates to assumptions on these lines. Okay? So such assumptions on the models that you are generating are called inductive bias. Right? So the whole paradigm of learning that we are talking about is called inductive learning, and the assumptions that allow us to get this kind of a generalization are known as inductive bias. Okay? And there are two forms of inductive bias generally. So one is called the language bias, which essentially is the restriction that we had on the kind of lines. If you say I'm going to only consider straight lines that are parallel to the x or y axis, that's one kind of a language bias. Or if you say that I'm going to consider only parabolas, that's another kind of language bias. Right? And the other kind of bias is search bias. Okay? So given that you have picked a language in which you're going to represent your classifier, how do you search among the possible classifiers in that language in order to find the right one? Right? And that again influences what kind of classifier that you're going to find, because you typically will end up with the first classifier that you find that has acceptable performance, and therefore that will be influenced by your search bias. Right? And we'll elaborate on this as we go along, and this is just to give you a feeling of what is involved in trying to do this kind of learning. So I'd like to elaborate a little bit more on the whole process of this supervised learning, right? And this is kind of common to the other algorithms you look at as well, but I'm just going to talk about supervised learning in a little detail in this module. So you start off with training data that is given to you. So training data consists of a vector x, right, and an output y. Right? So if you think about it, so in this example that we just saw on the previous slide, so x would be looking like the tuple of income and age, right? So the first data point could be that person has a 30,000 rupees per month income and he's 25 years old, and he did not buy a computer. And the second person had a 80,000 income, he's 45 years old, and he buys a computer. And so essentially you're going to have a series of data points like this that are given to you, and so you have to use your now your training algorithm in order to learn a classifier, right? But if you stop and think about it, so for us to be able to implement this in a numeric fashion, so you're going to have to encode your data. So you probably take your income levels and then do some kind of a normalization, right? So I've normalized it between 2 lakhs and 0 income. So and that gives me, like, the first person has an income of 0.15, the second person has an income of 0.4, and so on and so forth, right? And likewise, I have normalized the age between 0 and 100, and I get a numeric value for the age. And the labels are encoded again. So not buying a computer is now represented as -1, and buying a computer is represented as +1. So whether you use a -1 or a +1, or whether you use 0 or 1, or whether you can use y and n, right? It depends on the kind of algorithm that you are working with, and as we go along, as we see different machine learning algorithms, you will find you'll learn about the importance of the selection. Right? So once I have this encoded data, so the training algorithm is going to work on it, right, and it's going to produce a classifier. Right? But I need to know how good the classifier is, and I need to know if I can stop. Right? So if I go back on the training data and then ask how good the classifier is, typically we might end up overfitting the data, like I was showing you in a couple of slides ago. Right? So what we do is we set aside a testing set, right? So which is not something which was used to build the classifier, right? And then we validate the classifier on this testing set. And then if the validation tells us the classifier is good enough, then we can go ahead and output it. Or if the validation process tells us no, the classifier is not yet good, it's not yet good enough, and then I can go back and modify the parameters of my training algorithm or iterate over the data again until I converge to something that is acceptable. Right? There are many different ways when this validation can be done, and again we'll look at some of this later. So what exactly goes on in the training module? So the input, which is denoted by x, comes to the learning agent. The learning agent uses the current setting of the parameters, and it outputs a value, which is y hat, which is its guess of what the output should be for this input x. Right? And if you remember, in the training data, we already have a target y, which is the actual output that you expect from the agent. So I'm going to compare the target y with the guess, the agent output, which is y hat. That allows me to form an error, okay, which is the error in the prediction, and then it gets fed back into the agent, okay, and then the agent uses the error in order to modify its parameters. Right? So this is something which you've already seen to some extent in a regression setting, but we will look at more of a learning approach to regression in the next few classes, but you can also see that this is exactly what the classifier needs to do. Right? So there are many applications for classification. So there is credit card fraud detection, which is a very a few years back this was touted as a marquee application. Right? So when a person swipes a card, you can say whether there is a valid transaction or not. And the other application, which there's a lot of buzz around it nowadays, a lot of startups and many companies are focusing on it, is sentiment analysis, or sometimes called opinion mining or buzz analysis, etc. This is looking at social media data, whether they are tweets or whether they are blog posts, and so on and so forth, and then trying to figure out whether they are saying something positive about you or something negative about you. Right? So negative about, by you I mean whatever is of interest to you. It could be a movie, it could be a new album, it could be a product that was released. So instead of marketeers going door to door asking people what they feel about the products, they are now able to analyze the posts that people put in the public fora and automatically figure out whether the opinion is positive or negative. Right? Another application which has a lot of commercial impact is one on churn prediction. So a churner is somebody is your user from your service who is likely to leave. It's like, okay, I'm going to switch from Vodafone to Airtel, right? So, or I'm going to switch from a Windows machine to a Mac. So these people are churners. You know, they're habitual users of a particular service who are going to leave it and move to another service. So many companies are very interested in identifying such churners and then taking measures to retain them, right? Because attracting newer customers to your service is a little harder than keeping the customers that you already have, and people are willing to spend money to do that. So that is another interesting application. And of course, increasingly, medical diagnosis is proving to be a very fertile ground for classification algorithms. Though it's the medical community is really not in a position to completely accept what machine learning people tell them, but the machine learning people anyway keep working on a lot of medical domains, and there are many competitions that are run that ask people to build classifiers that can predict whether a patient is sick or whether a particular blotch that they see on an X-ray or a scan, whether that's a cancerous thing or whether it is benign. So all these kinds of diagnosis questions, right, are asked of machine learning algorithms. Right? There will be a fair amount of success, but then still quite a bit of way to go. And another place where machine learning is used in medical diagnosis is in risk analysis. So I'll elaborate it on a little bit more when I talk about regression. And there are in supervised learning, in fact, classification is one of the most widely studied machine learning paradigm. Right? So there are many approaches for classification, and some of them are very famous. I mean, a few of you might recognize the names here. Right? They can produce supervised learning can produce different architectures. So it could be artificial neural networks, which we will talk about later, support vector machines, decision trees, or just sets of rules. You know. And there are other popular methods such as nearest neighbor methods, where you remember all your training data, and then when a new data point comes in, then you try to make a prediction based on which of the training data looks like the new data point, right? And also probabilistic methods, typically based on a Bayesian approach to learning. So we will be covering at least the first three in this course in detail. The other supervised learning problem that we are going to talk about is regression or prediction, right? So here the data is going to have continuous outputs. So the input in this case, in this simple example I have, is temperature, right? So the x-axis is the time of day at which the temperature is measured, and the y-axis is temperature, which is the output. So you could see that typically daytime temperatures are higher and nighttime temperatures are lower. And now I can try and fit a curve to this, right? So ideally, what you would like to fit, well, all of us know about linear regression. So what we are going to do first is try to fit a straight line, right? But then you could try to be a little cleverer, okay? And you could try to fit a more complicated curve like that. That looks a little reasonable. Or you could overfit the data, like we talked about earlier, and then try to make the curve really complex, and then try to follow all the micro variations in the temperature, right? So obviously, in the night time, you see a data point that has temperatures almost as high as the daytime. That's a noise, right? But if you try to overfit it, you're going to get incorrect results. So we already looked at the regression in a little bit of detail, so that we know that we are essentially trying to minimize the sum of squared errors when you're trying to make a prediction. So how do I fit this line? I just figure out the difference between the line, the prediction made by the line that I fit, and the actual data point that was recorded, right? And take the square of the error and try to minimize that, right? So that's the typical approach that we use for fitting lines, right? So as we have already seen, with sufficient data, okay, doing linear regression is simple enough. It's just a set of matrix operations, right? But then if you have many dimensions, in the last slide our data had only one dimension. It's essentially what was the time of day, right? That was my x vector, right? But then if you have many dimensions, and then you really need a lot of data points in order to avoid overfitting. Because if I have like 1,000 dimension data and I have only 100 data points, it's very easy to overfit to those 100 data points because I have 1,000 parameters, right? So how do I avoid that kind of overfitting? Is by adopting something called regularization. So we will ensure that of all the models that can fit the data to a certain extent, we'll try to find something that is simple enough, right? So that we do not overfit the data. So we've been talking about linear regression, but suppose I want to do a higher order regression. So if you remember in the previous slide, so we looked at an example where so again it looked like a quadratic curve was a slightly better fit to the data than a linear fit, right? So how do we handle higher order functions? One simple way of doing this is to look at what are known as basis transformations. So where you take the input, right? So input could be say x1 and x2. There are two variables that describe the data, and then I translate that into a much larger description, right, by adding second order terms. So I take x1, x2, I create x1 squared, x2 squared, the product x1, x2, and then the original variables x1 and x2. Okay, now that gives me a 5-dimensional data. So I took the 2-dimensional data and I converted it to a 5-dimensional data. And now I can do linear regression on this 5-dimensional data, right? And this is going to end up giving me quadratics, right? So I can use the same technique of linear regression and I can get more complex fits by doing this kinds of basis transformation. So linear regression is not really that weak of a method because I can do more complex fits using linear regression, right? There are many different applications of regression. So the one thing which I already mentioned earlier was in time series predictions, right? So you could try to build a model that predicts rainfall in a certain region, or you could try to build a model that predicts how much money a user is likely to spend on a particular service, let's say calling, right? Sometimes you can even use linear regression to do classification, right? So instead of saying whether the person will buy the computer or will not buy the computer, you can try to predict what is the probability the person will buy a computer, and you can try to solve that as a regression problem. This is roughly, right? So I mean there is more nuances to that, right? And you can use regression as a data reduction tool. So instead of giving you like 100,000 data points, I can just fit a low dimensional line, low dimensional curve to that. That could be even a straight line, and then I can just tell you these are the parameters of the line instead of giving you the 100,000 data points, and that allows me to have a very large data reduction, right? And the other thing is to look at trend analysis, right? So it is slightly different from the time series prediction problem that I was mentioning earlier, because I'm not really interested in making predictions here, but I'm more interested in the data analysis part, not necessarily in the predictive analytics part here. So I would like to know whether the growth rate is linear or exponential, or somewhere in between. So those kinds of questions can be answered by suitably solving a regression problem, right? And then going back to what I mentioned earlier about risk analysis or in the classification case, right? So you could think of risk analysis here. So if you remember in linear regression, you learn coefficients for each of the input variables, right? So the input variable that has a larger coefficient is the one that's going to be influencing the output the most, right? So that way you can look at risk analysis by looking at the factors that contribute most to the output. So this is essentially on supervised learning methods. So we looked at two of these, regression and classification.